Hello everyone, this is Abhishek Mohanty and welcome to lecture number 5 of the chapter Electric Charge and Field. In the previous lecture, we had discussed about the superposition principle of Coulomb's law and then we had solved few numericals. Today, in this lecture, we will discuss about a new topic and the topic name is electric field and electric field intensity. So, let's get started. So students, we have heard the terms like electric field, magnetic field, gravitational field. So the question is, what is the meaning of a field? What is the meaning of field? Meaning of field. So to understand the meaning of field, let us go back to our lower classes. In class 8, we had categorized force into two parts. On the basis of their mode of operation, we have categorized force into two categories. So force can be divided into two categories on the basis of their mode of operation. The first one is contact force and the second type of force is non-contact force. Contact force and non-contact force. So what are the examples of contact force? When we are pulling an object, then that force, the pulling force, is example of contact force. When you are pushing an object, then that is also example of contact force. Similarly, the tension in class 11, we had studied about tension. When you are pulling an object through a rope or through a chain, that is the tension force. And when you are kicking a football, again that is example of the contact force. So why do we call these forces as contact force? Because there is a physical contact between the two bodies. We know that whenever there is an interaction between different bodies, there exists a force. And if the interaction is due to the physical contact between the objects, between the bodies, then that force is known as contact force. So these are the examples of contact force. Now let us come to non-contact force. So what are the examples of non-contact forces? Electrostatic force. The electrostatic force between two charges is example of non-contact force. The magnetic force between two magnetic poles, or the magnetic force between a bar magnet and a small iron piece. And the gravitational force. Gravitational force. So these are the examples of non-contact forces. So what is the meaning of non-contact force? Means the force which operate without any physical contact among the interacting bodies. For example, suppose you have 2 point charges Q1 and Q2 separated by a distance r in vacuum. So according to Coulomb's law, the electrostatic force between these two charged particles is given by F equal to 1 by 4 pi epsilon naught Q1 Q2 by r square. It means the charge Q1 exerts some force on charge Q2 and similarly charge Q2 also exerts some force on charge Q1. But there is no physical contact between the two charged particles. There is a gap between them. So although there is no physical contact, still the two charged particles are exerting force on each other. So this is the example of electrostatic force or the non-contact force. Suppose similarly, if you have a bar magnet and if you place a small iron nail, a small iron pin or iron nail near the bar magnet, then you will see that the iron nail will be attracted towards the bar magnet. Means the bar magnet will exert some force, a magnetic force on the iron nail. But here there is no physical contact between the iron nail and the bar magnet. But still there is a magnetic force. Again, this is example of non-contact force. Similarly, suppose you are standing on the top of a building and from the top you release an object. You will see that the object will fall down to the ground because we have gravity. The gravity attracts every object towards the center. That's why the object will fall down. Again, there is no physical contact between the earth surface and the object, but still earth attracts the object towards its center. So these are the examples of non-contact force. So now the question is, in case of contact force, there is a contact, physical contact between the interacting bodies. That's why the force is transferred to the force is transferred to the object. But here there is no physical contact. Then how does the force get transferred? That is the main question. So the answer to this question lies in the storm field. So remember that all the non-contact forces, they operate through a field. So what is the meaning of field? Field can be defined as the region of influence. The region of influence. Region of influence. So let us understand this concept in more detail. Suppose you have a bar magnet and you have a small iron nail. If you place that small iron nail near the bar magnet, then you'll see that the iron nail will be attracted towards the bar magnet. Is that clear? Now if you move the iron nail to slightly more distance, a large distance, slightly more distance, then you'll see that the bar magnet can also attract this iron nail, but with a small amount of force. If you gradually continue to increase the distance between the iron nail and the bar magnet, a time will come when you will see that if you place the iron nail at a very large distance from the bar magnet, then the bar magnet will not be able to attract this iron nail. Means there is no influence of the bar magnet on the iron nail. So we can say that the iron nail is outside the region of influence of the bar magnet, and that region of influence is known as field. If the region of influence is due to a magnet, it is known as magnetic field. If the region of influence is due to a point charge or a charged body, it is known as electric field. And if that region of influence is due to a mass, that is known as the gravitational field. Is that clear? So remember that field means the region of influence. And in this topic, we will discuss about the electric field. So I hope that you have understood what is the meaning of electric field. Electric field means it is the region of influence of a charged body. So let us define what is the meaning of electric field. The region around a charged body, the region around a charged body inside which its electrical effects can be experienced is known as electric field. The region around a charged body inside which its electrical effects can be experienced is known as electric field. So now the question is, what is the meaning of these electrical effects? So we know that whenever we have two charged particles, there is a Coulombic force. The Coulombic force may be attractive, it may be repulsive. So this electrical effect refers to the force, the interaction between the charges. Suppose I will place a charge q here. A charge small q is placed at the point O. Then you'll see that before placing the charge q at this point, the nature of the space, the nature of the region around the point O was different. But once I have placed the charge q here, the property, the nature of the region around this point will change. Because whenever I will place a charge at a given point, an electric field will be set up. an electric field will be created around that point. And that electric field means the region of influence of the charged particle or of the charged body. Suppose I will make a boundary. Suppose within this boundary the electric field exists, and outside the boundary there is no electric field. It means inside this region, the electrical effect of this charge can be experienced. Again I am repeating, if I will make a boundary, suppose within this boundary we have electric field and outside the boundary there is no electric field. It means inside this region, the electrical effect of the charge can be experienced. But you cannot see the electric field. You cannot see electric field, you cannot see magnetic field, you cannot see the gravitational field. These are invisible to us. So the question is how to determine whether in a given region electric field exists or not, magnetic field exists or not, gravitational field exists or not. So for example, suppose I will give you a small bar and I will ask you to determine whether this is a magnet or not. Then what will you do? You will bring a small iron piece. If the iron piece will be attracted towards this bar, then you will be sure that this is a magnet. But if the iron piece will not be attracted towards this bar, then this is not a magnet. So to determine the magnetic field, you have to take the help of an object which reacts to or which interacts with magnetic field, and that may be a small piece of iron or that may be another magnet. Similarly, to determine whether electric field exists or not, we have to take the help of an object which reacts to or which interacts with electric field. So remember that a charged particle reacts to or interacts with an electric field. Let me write this point. A charged particle interacts with an electric field. It means, suppose in this region I have electric field. Now if I bring another charge and place that charge at any point within this region, then that charge will experience a force. Again I am repeating, if you place a charged particle inside an electric field at any point inside the electric field, then the charged particle will experience a force. So if the charged particle is experiencing a force, then you will be sure that electric field exists in that region. But if there is no force acting on the charged particle, then you will be sure that there is no electric field in that region. So in order to determine or in order to test the presence of electric field, we have to take the help of another charge, and that charge which helps us to test the presence of electric field is known as test charge, and the symbol of this test charge is Q0. The symbol of the test charge is Q0. So test charge means it is the charged particle which helps us to test or to verify the presence of electric field in a given region. And by default, by convention, the test charge is always taken to be positive. The test charge is always taken to be positive. By convention, we always take the test charge to be positive. There is no reason behind it. Why do we take test as positive, not negative? There is no reason behind it. By simple convention, we have taken the test charge to be positive. Is that clear? And another important property of the test charge is its magnitude. The magnitude of the test charge is very negligible, as compared to the source charge, source charge. So there are two important properties, important points about test charge that you should remember. The first one is the test charge is always taken to be positive. You cannot take the test charge to be negative. By convention, we always take the test charge to be positive. That is the first point. And the second point is that the magnitude of the test charge is very negligible as compared to the source charge. So what is source charge? Source charge is the charge of which the electric field is being studied. Now we are studying the electric field of this charge. This charge Q is placed at the point O and we are studying the electric field of this charge. So this charge small q is known as source charge. Source charge means the charge whose electric field is being studied. Source charge means the charge whose electric field is being studied. In this example, we are interested in studying the electric field of this charge Q. So this is the source charge. And to test the electric field of this source charge, we have to take the help of a test charge. And the symbol of the test charge is Q naught. Is that clear? And Q naught is always positive. And the magnitude of Q naught is very negligible or very small as compared to that of source charge. For example, if the source charge is 1 millicoulomb, then you can take the test charge to be 1 nanocoulomb. 1 nanocoulomb is very negligible as compared to 1 millicoulomb. So the question is, why should we take the magnitude of test charge very negligible as compared to the source charge? The reason is that every charged particle, every charged body creates its own electric field. Is that clear? Every charged particle or every charged body creates its own electric field. So in this problem, we are interested to study the electric field produced by this 1 millicoulomb charge. Is that clear? And to find the electric field due to this 1 millicoulomb charge, we have to take the help of a test charge Q naught. And when you place the test charge Q naught inside the electric field of the charge Q, then what will happen? The test charge Q naught will also create its own electric field. We are interested to study the electric field of the source charge. But when you are verifying the presence of electric field, you have to take the help of test charge. And when you place the test charge inside the electric field of the source charge, then this test charge will also produce its own electric field. So the electric field of source charge and electric field of test charge, they will interfere with each other. Again I am repeating, when you place test charge inside the electric field of a source charge, then what will happen? The electric field produced by the source charge and electric field produced by the test charge, both of them will interfere with each other. And if the magnitude of test charge is not very negligible as compared to the source charge, then the total electric field will be disturbed. But if we take the magnitude of test charge to be very small, very negligible, then the electric field produced by this test charge will also be very negligible, very small as compared to the electric field of the source charge. That's why the interference can be neglected. We can neglect the contribution of electric field due to the test charge. But if test charge has magnitude comparable to the source charge or more than the source charge, then the electric field produced by the test charge will change the entire electric field of source charge. So in order to avoid this discrepancy, we always take the magnitude of test charge to be very negligible or very small, because we are not interested to study the electric field of test charge. We are interested to study the electric field of the source charge. Is that clear? So this is all about electric field. Electric field means this is the region around a charged body inside which its electrical effects can be experienced. Is that clear? Now, this electric field, the strength of electric field is given by or is represented by a vector quantity, and its name is electric field intensity. The strength of electric field is represented by a vector quantity known as electric field intensity. So now we will discuss about what is the meaning of electric field intensity. So we know that if you place a test charge inside an electric field, then the test charge will experience a force. Now let us define the term electric field intensity. Electric field intensity, E vector. So how can you define it? Electric field intensity, electric field intensity at a point inside an electric field, inside an electric field may be defined as the electrostatic force per unit positive charge placed at that point. Again, I am repeating the definition. Electric field intensity at a point inside an electric field means if we have electric field in a region, then at a given point I can find the electric field intensity. Then how to find it? The electric field intensity at a point inside an electric field may be defined as the electrostatic force per unit positive charge placed at that point. Suppose in this region we have an electric field and we have to calculate the electric field intensity at this point. We have to calculate the electric field intensity at this point. Then how to define it? The electric field intensity at any point inside an electric field is defined as the force per unit positive charge. Force per unit positive charge. Force per unit positive charge. Or we can say that force per coulomb. Force per coulomb. Which force? Electrostatic force. Electrostatic force per coulomb. So we know that if you place a test charge to test or to verify the electric field, we have to take the help of test charge. So if you place a test charge at any point inside electric field, then that test charge will experience a force. Suppose I will place a test charge Q0 at this point. Okay, I will place a test charge Q0 at this point, and if the test charge will experience a force F, suppose the test charge will experience a force F, then on the charge Q0 force is F, on the charge Q0 the electrostatic force acting is F. Then what is the force acting on 1 coulomb, or what is the force acting on unit charge? Force on Q0 is how much? F. So what is the force on unit charge? Force on unit charge will be F by q naught. Force on unit charge will be how much? It will be F by q naught. So this force per unit positive charge is known as the electric field intensity. So I can write that E vector means electric field intensity. This is equal to F vector by q naught. F vector means the force acting on the test charge placed at their given point, and q naught is the magnitude of the test charge. So E is equal to F by q naught. So from this formula you can find the unit and dimension of electric field. So what will be the SI unit of electric field? The SI unit of electric field will be Newton per coulomb. Force can be expressed in terms of Newton, and charge can be expressed in terms of coulomb. So the SI unit will be Newton per coulomb or Newton coulomb inverse. So the SI unit of electric field is Newton coulomb inverse. And what is the dimension of electric field? The dimension of electric field is, we have force by charge. So force is m1 L1 t minus 2, and charge means current into time, so that will be a1 into t1. So the dimension of electric field will be m1 L1 t minus 3 a minus 1, m1 L1 t minus 3 a minus 1. So this is the dimension of electric field, and this is the SI unit of electric field. And look at this expression, E vector is equal to F vector by q naught. Here force is a vector quantity, charge is a scalar quantity, and this electric field is also a vector quantity. So the direction of electric field is same as the direction of electrostatic force acting on the test charge. Again I am repeating, the direction of electric field is same as the direction of electrostatic force acting on the test charge. So this is the formula for electric field intensity. How to calculate electric field intensity at a given point? E equal to F by q naught. So if E equal to F by q naught, then F equal to q naught into E. If E equal to F by q naught, then F equal to q naught into E. It means, suppose at a given point, the electric field is 3 into 10 to the power 3 Newton per coulomb. Suppose at a given point the magnitude of electric field is how much? 3 into 10 to the power 3 Newton per coulomb. And at that point, if a test charge or a charge particle of charge 2 microcoulomb is placed, if I place a charge of 2 microcoulomb at that point, then what will be the magnitude of force? What will be the magnitude of electrostatic force acting on that charge? The formula is charge into electric field. If you know the value of electric field at a given point, then the force acting on a charged particle at that point will be given by the product of the magnitude of charge and electric field. So F will be equal to q naught into E. Q naught is 2 microcoulomb. So 2 microcoulomb means 2 into 10 to the power minus 6 coulomb into electric field E is 3 into 10 to the power 3 Newton per coulomb. So this will be 2 into 3 is 6 into 10 to the power minus 3 Newton. Okay. So if the magnitude of electric field is given at a point, and if you place a charge at that point, then how to calculate the electrostatic force acting on the charged particle? This is the formula, F equal to charge into electric field. So now we will derive a formula to calculate the electric field due to a point charge. Let us find a formula to calculate the electric field due to a point charge. So we had discussed that electric field intensity at a given point can be defined as the force experienced per unit positive charge. So let us calculate the electric field intensity due to a point charge. Electric field intensity due to a point charge. Suppose I have placed a point charge Q at point O. Is that clear? And when I place the charge Q at this point, around the charge an electric field will be created. Around this charge an electric field will be created. And inside the electric field, I will choose a point P. I will choose a point P which is at a distance r from the charge Q or from the point O. Is that clear? So I have to find a formula to calculate the electric field intensity at a distance r from a point charge Q. Then how to calculate it? We know that the basic formula to find electric field intensity is E equal to F by Q naught. Electric field intensity is equal to force per unit positive charge. So let us put a test charge Q naught. Let us put a test charge Q naught at that point P. We are interested to calculate electric field intensity at the point P, so we have placed a test charge Q naught at that point P. Now, what will be the force? What will be the force on Q naught? We know that this Q naught will experience some force due to Q. This Q will exert some force on Q naught. If Q is positive, then the force will be repulsive force, because Q naught is always positive. The test charge is always positive. Q naught is always positive. If the source charge is positive, then the source charge will repel the test charge. But if the source charge is negative, then it will attract the test charge. But there will be electric force. Is that clear? So force on Q naught will be how much? F equal to 1 by 4 pi epsilon naught Q into Q naught by R square. Assume that the two charges are placed in vacuum or free space. Then the force on Q naught is how much? F equal to 1 by 4 pi epsilon naught Q naught by R square. This is Coulomb's formula, Coulomb's law. Then what is electric field intensity? Force per unit positive charge, F by Q naught. So if F equal to 1 by 4 pi epsilon naught Q naught by R square, then what will be F by Q naught? F by Q naught will be 1 by 4 pi epsilon naught Q by R square. Take this Q naught to left side, it will be divided here. So F by Q naught will be how much? 1 by 4 pi epsilon naught Q by R square. And this is the formula to calculate the electric field intensity due to a point charge. For example, let us solve a question. Calculate the electric field intensity at a distance 5 centimeter from a charge 10 millicoulomb. We have to calculate the electric field intensity at a distance 5 centimeter from a charge 10 millicoulomb. So how to calculate it? E equal to 1 by 4 pi epsilon naught Q by R square. This Q means the source charge. This is the source charge. The value is 10 millicoulomb. So the value of 1 by 4 pi epsilon naught is 9 into 10 to the power 9. And what is the magnitude of charge? 10 millicoulomb, and you have to express it in coulomb. So 10 milli means 10 to the power minus 3. So 10 millicoulomb means 10 into 10 to the power minus 3 coulomb divided by R square. What is R? R is 5 centimeter. R is 5 centimeter, but we have to express R in meter. So 5 centimeter means 5 into 10 to the power minus 2 meter. And we have to give a square because we have the formula 1 by 4 pi epsilon naught q by r square. This is equal to 9 into 10 to the power 9, and this one will be 10 to the power minus 2 divided by 5 square will be 25 into 10 to the power minus 4. Okay, and the unit of electric field intensity will be Newton per coulomb or Newton coulomb inverse. So this will be how much? 9 by 25 into, this will be 10 to the power 9 into 10 to the power plus 4 means 10 to the power 13 into 10 to the power minus 2. So it will be 10 to the power 11 Newton per coulomb. So this is the way to calculate the electric field intensity due to a point charge. Is that clear? So you can see that, look at the formula. The electric field intensity also depends on the distance from the charge. If we have a point charge, then if you go away from the point charge, then the value of electric field intensity will decrease, because E equal to 1 by 4 pi epsilon naught q by r square. In the denominator we have r square. If the distance increases, then the electric field intensity will decrease, like Coulomb's law. If you increase the separation between the 2 point charges, then the electrostatic force between them will decrease. If you make the distance double, then the force becomes 1 by 4 times. If you make the distance 3 times, then the force becomes 1 by 9 times. Similarly, the electric field intensity varies inversely as the square of the distance from the point charge. So if you draw a graph between electric field versus the distance, the graph will be like this. With increase in distance, electric field decreases. Is that clear? So this is all about electric field and electric field intensity. So I hope that all of you have understood what is the meaning of electric field, what is the meaning of test charge, and why should the magnitude of test charge be very negligible as compared to source charge, what is the meaning of the term electric field intensity, how to calculate electric field intensity at a given point, and the formula to calculate electric field intensity due to a point charge, and the dependence of electric field on the distance. So that's all for today's class. In the next class, we'll discuss about the continuous charge distribution and how to calculate electric field in case of continuous charge distribution. So till then, bye bye and have a nice day.